In this video, we are going to combine SymCC together with the AFL fuzzer. And the reason you would do this is essentially to get the best of both worlds. So we want these introspection capabilities and the path constraint solving capabilities from symbolic execution. And then we also want to have this depth and efficiency that fuzzing gives. And this will be a practical demonstration, so at the end of this video there should be a clear understanding of where the benefit, or an example of the benefit from combining these two. And the official documentation of SymCC has a fairly good guide on how to do this. So that is placed right here, and you can see that in the official repository, where they have a guide on how to combine SymCC with a fuzzer. And we will essentially, what we're going to do in this video is to follow these steps, but we will have made just a few slight modifications. So the first thing we're going to do is we're going to compile SymCC as well as AFL and various dependencies. And where we previously used SymCC by way of the Docker image, we are now going to install it on our host. And the reason for this is partly due to shortly we will be starting to modify SymCC, and also because it's a little bit easier to run multiple processes when we are outside of Docker images. So we take this build system here, so this build file, and it's simply just a bash script that we will execute. So let's create a directory called AFL SymCC combo. And let's just go in here, and then let's create our install script. Okay. And what this install script will do is it will install a various set of packages. And where we previously have used a more modern version of Clang and LLVM, we're going to use Clang version 10 as well as LLVM 10 here. And then we need to install a few different packages such as Z3, AFL, SymCC, and that's essentially it. Okay, so let's just execute this script. And we should be good to go now. This will take a while, so I already had a bunch of the headers installed, but this will still take a while, and especially the compilation of Z3 can take quite a bit of time, so I'm going to resume this video once it has completed. Okay, so the script now finished, and everything went all right, except for beware that as it currently stands, there are some of the tests that will fail. And for example, if we go up to here, we can see that when compiling, when running some of the SymCC tests, you will see that some of them actually fails. And don't worry about this; it won't be an issue at all. And I went through the issues of SymCC, and it seems to be that some of the tests were written for big endian architectures and not little endian architectures. Okay, so what we're going to do now is, so now we have installed, as we can see, various different versions of SymCC, and we also have AFL in here. And we are essentially ready to get started with doing our experiment. So what we're going to do is we will take this application. Oh, one final thing we have to do is we have to compile and also install a tool called SymCC Fuzzing Helper that exists within the SymCC repository. And this is a Rust application that we need to use, which will be the one responsible for managing the collaboration between AFL and also SymCC. And the way to do that is simply going into the SymCC source and then running this command. And this should be fine. And then when that has completed, what we're going to do is we're going to try and analyze this small program. Okay, so it now finished. And what we're going to do now is we will make a small folder where we will be doing our experiment. So let's create the folder ex1, and then we're going to copy our application into it. And as you can see, it just has a simple main file together with a foo function. And what this small application does is that it opens a file, and this file, the name of this file is given by the first command line argument. That is not the name of the application. And then it essentially just reads the contents of this file into a variable called string. And then we pass that string into the foo function here together with argc -2. So if we give a file name here to the command line, this will evaluate to 0. So t1 up here will be evaluated to 0 if we give a single command line argument, because then argc will be 2. So what happens in this function is a bunch of checks are done on the array we have here. So we will just be checking a few integers here and return in case these are equal. And then afterwards we will do an equality check here of the first 4 bytes in this array that we pass, whether they're equal to dead beef. And if they are, we will return 0. If they are not equal to dead beef, then we will return 0. Otherwise, we are going to return 20 divided by t1. So in the case where t1 is equal to 0, this will throw a division by 0 error and will effectively crash. So what this means is if we get to here, the first 4 bytes of the R argument needs to be equal to dead beef. And that means that the file down here has to contain the dead beef characters as the first 4 bytes. And this is the part where we will struggle with the fuzzers to get past this point, but SymCC will be able to analyze this instantaneously, and thus having the combination of the two will be able to get past these very quickly. And what we're going to do now is we're going to show that launching a couple of fuzzers and having them run for a while will not trigger the crash that will occur down here. But then when we combine the 2 fuzzers with SymCC, we will very quickly see a crash because SymCC is going to resolve this very, very quickly. Okay, so let's exit this application. And what we now need to do is we need to compile this application in multiple ways. We need to compile it both with AFL, and we also need to compile it with SymCC. So we will have 2 different binaries. So let's just copy this command here that will use the AFL we just installed as follows. So now we have a binary here called AFL int check, which is the compiled version of our int check application. And then we're going to compile the same int check file here and with the SymCC compiler. Okay, so there we have this, and we now have 2 different executables, one for SymCC and one for AFL. And what we now need to do is we need to run these binaries. The first thing we do is we create a corpus. So let's just create a folder here called corpus, and then we're going to put a seed into this folder. Okay, so now we have our setup in terms of we have a corpus here, which is just a single seed file with a lot of uppercase A's. And what we're now going to do is we're going to launch a few instances of AFL. We will launch a master as well as a secondary, and then we will run these AFL fuzzers for a while and see what's happening. And then after a while, we will also launch a SymCC instance. But before we do that, we just need to also include the directory of the AFL binaries in our path variable. And the reason for this is when we're going to launch this SymCC instance in a moment, the SymCC fuzzing helper, that binary will use some of the binaries that exist within the AFL folder. So let's just navigate into the AFL folder where we have these binaries, and in particular this show map, we need to use that one. So let's just get the path of this, and now we should be able to quickly put this into our path variable. So let's do that as follows. And we're also going to open a new terminal because we will launch multiple instances of of AFL, and we're going to have those in 2 different terminals. So let's create 3 windows here. and move into the same folders, ex1 and also AFL ex1. And I'm just going to zoom out a little bit because we will have to display some graphics here, and that requires a little bit of space. I can also try and make it a little bit larger. As follows. Okay, so let's just create the paths as well here. Okay, now we are going to launch first an AFL master instance up here. And the way we'll do that is simply use the following command. As follows. And now AFL should start in just a moment. And we can see now AFL is running, and it is running against our AFL int check binary. So our binary is now being fuzzed. And we can see that there are no crashes so far. I'll also start the secondary instance as follows. And now we should also see that graphic come up in just a moment. And that graphic is now running. And now I'm going to let these run for a while, just to show that nothing is actually happening. And then when they have run for a while, what we're going to do is we're going to launch this command, which will start to use the SymCC in combination with our AFL instances, such that the SymCC, SymCC fuzzing helper will look at the seeds generated by, or like the corpus generated by the AFL instances, and then it will run on instances that are, then it will run SymCC on those inputs, and then if it finds new inputs that trigger new paths that seem interesting by looking at the output from AFL show map, then it will pass these interesting inputs into the queue of AFL. So in this sense, this SymCC fuzzing helper will start to manage the combination of these two by intersecting the seeds running with SymCC and those with AFL. And if any interesting new seeds are found by SymCC, it will also pass these inputs over to the AFL instances. Okay, so I will just leave this running for a little bit and then resume the video after a while. Okay, so the AFL master instance here has run for 3 minutes, and we can see that there are no crashes. So now we're going to execute this command, which will launch SymCC in collaboration with the AFL instances. So we'll simply paste this into our folder, to our terminal down here. And once we run it, keep an eye out on these unique crashes here, as they will change when we launch the SymCC instance. Okay, so SymCC is running now, and we can see almost instantly we found the crash, or a crash at least. So let's just exit these, and let's also exit this one, and then let's just look at the crash that was generated by, or the input that was generated by SymCC and what crash it caused. Let's look at the content of that file. And the content will simply exist within the AFL out folder as we would expect, and also AFL master here inside of crashes. And there we can see the file here that caused the crash. And we can see that it is 4 bytes, which is good because remember that we were only looking at the 4 bytes here. So if we look at what is the content of this file, then we can see that indeed we have dead beef here in little endian order, and SymCC was effective in finding a new input that the AFL instances had trouble with, and then passing that input over to the AFL instances running, and the AFL instances were put the crash inside of their own crashes folder. So that's how the combination of SymCC and AFL works on a very simple case, and also highlights one of the strengths of combining the two. In the next video, we will start to look more into the code of SymCC, and we have now passed kind of like the practical demonstrations, this like black box inspection of how the tool works, and we should be ready to get a little bit more into understanding how the LLVM structure around SymCC is designed. So, thanks for now.